Okay, should we get started?
Yep.
Okay. Looks like we have a good turnout. Welcome everyone to this week's CDAC webinar talk. It's a pleasure to introduce our colleague, Bianca Haberl, today. Bianca is a versatile high-pressure scientist. She's a staff scientist now at the Neutron Scattering Division of Oak Ridge National Laboratory. Bianca received her degrees in physics from Augsburg in Germany before moving to Australian National University in Canberra, where she obtained her PhD also in physics in 2011. And she remained there for a couple of years as a postdoc and then received a prestigious Weinberg Fellowship at Oak Ridge, moving there in 2014, and in 2016 joining the staff of the Neutron Scattering Division. And since going to Oak Ridge, she's been very active in promoting high pressure neutron scattering, also X-ray scattering. She's been active in the Neutron and X-ray Scattering School and is involved in beamlines or instruments there dedicated to high pressure science. And this includes the new initiative for possibilities at the second target station. So we're delighted she's joining us, and her talk, you can see, is high pressure neutron scattering, hydrides, and group 4A materials. Welcome.
Okay. Well, thank you so much for the introduction, Russ, and thank you for inviting me here to speak. It's really my pleasure to talk a little bit about some of the high pressure neutron scattering efforts we are pushing in Oak Ridge, and to talk about some of our specific science examples on things that are really going on at the moment. So as Russ already alluded, I'm working with a large range of people. So let me first acknowledge my co-workers, please, because I could not possibly fit everyone on the front screen or on the that line. So of course, the SNAP team is very involved with all the high pressure work. You may know them, Antonio, Jamie, and Chris. We also work very closely with Malcolm. He, of course, used to be located at Carnegie, but has now moved to Sweden. Then one key member of the high pressure efforts is Raini, who is really the mind behind behind all the diamond anvil cell development that I'm going to talk about later. And then I would also like to acknowledge the vision team, which are involved in some of the germanium work, the basis team, which I will talk about a little bit later when I'm talking about hydrogen diffusion, Mary Ellen, who is a postdoc who joined us a little bit over a year ago, and she is managing to do experiments even now with all these restrictions we have. And then, of course, our sample environment support crew that is really invaluable in getting things done. So for those of you who have not been to Oak Ridge, we are located in the hills and valleys of East Tennessee, close to Knoxville. We have two user facilities, the spallation neutron source you see up here, and the high flux isotope reactor, which is down here, which in total have about 30 instruments you can pick from that offer quite a large variety of different neutron scattering techniques. So I thought in this talk, I really wanted to focus on some of the high pressure capabilities we've been developing and some of the science we have been doing. So I am not planning to give much background on the neutron scattering itself. I appreciate that neutron scattering can be a bit of an exotic beast. At least it was to me before I came to Oak Ridge, since, as Russ was mentioning, my background was more in X-rays. So if you are interested in learning a little bit on the background on different neutron scattering techniques, I can actually recommend this year's Neutron X-ray Summer School. Due to COVID, it was virtual, and so all the lectures have been recorded and are available online to anyone. So yeah, please feel free to check it out. And yeah, with this, let me sort of just explain the outline of my talk. I decided to focus on 4 different high pressure efforts that we are sort of emphasizing at the moment. High pressure neutron diffraction on SNAP, where I will then also mention some of the recent hydride work I've been doing. Then I want to talk a little bit about some of the quasi-elastic neutron scattering we've been doing on basis, and particularly the work by one of our PhD students or former PhD students, Eric Novak. After that, I want to talk about inelastic neutron scattering on germanium. For those of you who know me, I've been very interested in group 4A materials, so this is really a recent topic I'm very excited to push. And finally, I want to show you some of the really exciting neutron spectroscopy we've done on hydrogen. So let me just change my pointer. Okay. So for those of you who are not familiar with the SNS, we have a dedicated high pressure time of flight diffractometer SNAP at the SNS. In Carnegie has been very involved, especially E3 has been very involved in pushing diamond anvil cell development there. And it's really, it's really the instrument that is dedicated to high pressure and where you can push the limits and where you can achieve the highest pressures possible with neutron scattering. They've recently had an upgrade just in March this year with an entirely new neutron focusing optics, and we are still learning what is possible, but it really seems to be remarkable how improved things are and how much more we can do now. So just as a very brief background on why neutron scattering or neutron high pressure scattering is always so different from X-ray scattering. And that is really simply due to the fact that even with the brightest sources, our flux is still a lot smaller than what you have in a synchrotron. So if you think about your standard diamond anvil cell, as you may use it for X-ray diffraction or Raman or any other in situ study, really, 200 micron QLEDs are sort of, a good size for quite a range in pressure. So your sample would be a maximum of 100 microns across. Now, to translate this to neutron sizes, most high flux neutron instruments, with the exception of SNAP, really, have a minimum size they can detect of 1 cubic millimeter on the sample. So this really translates to a sample size that's a little bit larger. Now, since we all know pressure is force over area, if we want to get to the same pressures as we do for a normal diamond anvil cell, we need a lot more force if we want to do the same thing with a Neutron DAC. And this is really where all the complication comes in. And this is really why we have so many different types of cells, why we keep on developing, and why our cells are also a little bit larger. So on SNAP over the last 5 years, we have developed neutron diamond cells that are based on very, very large CVD anvils. These cells have become what we call the standard DAC for SNAP. Pressure can be increased online, so we have membranes the same way you have for the X-ray diamond cells. The cells can be cooled down to 5 Kelvin, and up to 40 GPa is often a comfortable pressure regime. So I can imagine Antonio shaking his head right now because he's had some bad luck lately. One of the key points of this development were that we were able to get very, very large CVD anvils. So these here are 6 millimeter conical anvils as we typically use them on SNAP. The conical design has been key so that we had this added radial support to achieve the high loads of up to 10 tons that we need. We did test normal cylindrical cells in the beginning, anvils in the beginning, and we cracked them in half at 3 tons, which really hurts when you break a 10-carat diamond. Another development has been in the gaskets, which really need to give more radial support to the diamond as well. So they have been preformed, or we are making now gaskets that are made from several parts to really give the diamonds the optimal support so we can get to these 10 tons we need for high pressure on neutron-sized samples. So just a few examples over the years. So nickel is always a good sample to sort of explore what is possible. And we can really see these samples in what's for neutron scattering very short times. We can also see more complex samples now, like for example, octadecane, which was work done with Abhishek Basu, who used to be at Carnegie. And then recently, Malcolm Guthrie has been pushing I7 to 60 GPa. Now, you may recall that in past works, they have reached higher pressures, but the contrast here is that these new diamond cells give a lot larger scattering aperture. So now we actually have sufficient data quality for full Rietveld refinement. So I believe these 62 GPa are still the record for the highest ever neutron refined data. Now, of course, I was also a little bit self-motivated in all this development of these diamond anvil cells. Because one of the things I really wanted to study when I came to Oak Ridge was amorphous silicon in the presence of hydrogen. So as you all know, there has been the prediction by Neil Ashcroft that compression of silane may give access to the metallic state of hydrogen. And so quite a number of studies have attempted to pressurize silane, which is non-trivial. Raini and I did an attempt once, which involved a flaming cell at some point. So we've been trying to think of other ways to do that. And if you look at some of the high pressure studies on silane, it appears that about 60 GPa, you actually end up with a hydrogenated amorphous phase. Now, this is something we could synthesize at ambient and then pressurize. Instead of starting from silane, we could start from amorphous silicon and hydrogen. Could this act as a precursor material? So after 5 years, I finally got to do this experiment last year. We loaded amorphous silicon with D2 at SNAP and pressurized it at low temperature to avoid our diamonds breaking. And here you see the result of the diffraction data from SNAP to 20 GPa. And we see quite clearly hydrogen. So these here are the characteristic hydrogen peaks. They shift with pressure as you would expect, but we did not see any reaction with the amorphous silicon, unfortunately. Incidentally, this is probably one of the best powder samples of hydrogen ever made. So the data are still really interesting, but they did not show any of these syntheses I would like to see. So obviously we need hydrogen compatible cells that we can push to higher pressures. We did not go higher than 20 because we had a massive blowout on the diamonds and they all turned to dust. And we also need better anvils that really can withstand hydrogen even when you have such a large surface as you need for a neutron diamond cell. So just as a, I don't know, teaser, I guess, Raini has started developing, again, entirely new cells that will tackle this problem. They are based on smaller gem quality CVD anvils. And just a few weeks back, we did the first test with these new cells and new anvils on SNAP. Again, as the testing material, we chose nickel. And so here you see diffraction data from nickel. It was a very small sample. I believe it's the smallest sample that has ever been measured on SNAP, and so presumably with any neutron diffractometer. We still got good data after fairly short exposure time, so this is extremely promising. And depending on the equation of state you use, we are just at 100 GPa or even a little bit above. Now, given the good data quality after such a short time, we are, of course, are now pushing for smaller samples and higher pressures. So this will, yeah, please stay tuned. We hope to report on breaking the Megabar pressure limit by quite a lot at some point later this year. Wish us luck. Okay, so with this, I would like to move on to quasi-elastic neutron scattering and give an overview over some of the work we have been doing at BASIS. Quasi-elastic neutron scattering basically looks at very small momentum transfer. So it looks at things that are happening right next to the elastic line, which are sensitive to hydrogen dynamics and diffusion, for example. So here you see an image of the tank at BASIS. So this here is several stories tall. It's a very large tank. And the work there involved quite a number of people. It involved the BASIS team, of course. Then Eric Novak, who was doing his PhD work on that study I will talk about later on barium hydride. And then, of course, it also involved Luke Damon, who was supervising Eric, and Jamie and Mark and Matt to get things going. So in an initial test, it all started by us pushing high pressure in the very small PE cell. So that so-called VX1 PE cell is only about that large. So it can be very easily dangled off a long stick into that large tank you saw on BASIS. And what we did is simply adopting an idea that was published by Stefan Klotz. Now, for quasi-elastic neutron scattering, for a lot of studies, it's really critical to avoid any multiple scattering. So sample sizes there are a bit unusual. You don't have a normal sample palette. Instead, most of the samples are annulus. And this is something that can actually be replicated in the PE cell, which supports the large sample volumes by having extra toroids. So here you see an image of these gaskets we used. It's a split gasket. Usually your sample would sit in the center here. But for the quasi-elastic neutron scattering, we put the sample in that groove out here so that we were able to maximize the sample volume by still keeping the sample really skinny. And on our first experiment with this VX1 PE cell, we did achieve 1 GPa on an ionic liquid. But that small press could not apply any higher load. So we were really stuck at 1 GPa. So this is ongoing work to push and increase the pressure range, because obviously 1 GPa is interesting for a lot of studies, but not that super high in pressure. So luckily then last year, Eric got very interested in QENS and high pressure QENS in particular on barium hydride. As you probably all know, such metal hydrides as barium hydride are very interesting materials for solid state hydrogen storage. Barium hydride in particular seems to have many advantages, which is why it's studied in detail. What is quite interesting about it too is that it has two distinct polymorphs, orthorhombic and a hexagonal polymorph, that exist, that can be accessed through high temperature and high pressure. So the low temperature, low pressure polymorph is the orthorhombic structure. And then if you heat, but also if you pressurize, you obtain a hexagonal structure. So this really makes for a lot of interesting studies where you can look at the temperature dependence and compare it to the pressure dependence. So Eric's work showed indeed that in a temperature-dependent QENS study on this barium hydride, that there was very interesting distinct jumps in the diffusive motion. And looking through the literature, it also appears that the ionic conductivity increases a lot in the hexagonal phase. So here you see some results from impedance spectroscopy from the literature, where quite distinct differences were seen in the low pressure orthorhombic phase and the high pressure hexagonal phase, which is this white regime here. Interestingly, it didn't seem to correlate directly with the phase transition. It really seems to have ramped up at higher pressure within the hexagonal phase. So with this as motivation, trying to see how we can correlate the temperature dependence and the pressure dependence, Eric set out to study barium hydride with neutron scattering. Although there have been quite a number of X-ray studies, we did want to get some better insight into his particular samples using neutron diffraction. So he performed an initial experiment on SNAP, where the barium deuterate was loaded in the normal PE cell and pressurized to 10 GPa. So here you see a typical diffraction pattern taken at ambient pressure in the orthorhombic phase, and here the new hexagonal polymorph that appears at high pressure. We paid a lot of attention to these pressure load curves for the normal gaskets, but also for these special gaskets that were used for bases, because they were used in the end to extract the pressure for our particular basis experiments. So with this, Eric had a good sort of understanding for how to pressurize the barium hydride and how to study it. And so we moved on to adapt this to bases. As I mentioned before, with this very small PE cell, we were really limited in pressure to 1 GPa. So we upgraded to the so-called VX5 PE cell, which, despite the name, is actually the middle-sized PE cell, which can routinely achieve 10 GPa in a sort of standard setup with the so-called single toroidal anvils. So here you see an image of that cell. It's sort of that big, you can just pick it up, or I can just pick it up. Others may find it easier. Additionally, you see a special clamp in there. The barium hydride has, of course, needs loading in a glove box. So you can't just load it in air, otherwise you will not have barium hydride any longer. So this entire setup was then hung on this flange setup into this large basis tank. And so additionally, we of course added a blast shield to ensure everything is contained in case of a blowout. Now, blast shield is it's a fancy phrase for this because this was initially an aluminum pot we obtained from McMaster. So with this, we then measured the barium hydride up to 7 GPa using high pressure QENS. I believe this is the highest pressure that has ever been attempted for QENS. And so here you see the resulting data. The black curve here is the ambient pressure data, which is used to obtain the instrument resolution, since essentially the hydrogen motion is frozen there. And then as pressure increases, we see this quasi-elastic broadening. And this is directly related to faster dynamics. So it was not possible to extract meaningful data from the 5 GPa data, possibly because we were still in an intermediate regime in phases. But at 6 and 7 GPa, we quite clearly see a decrease in the timescales. So this is very encouraging, but unfortunately, we did not get to this point in pressure where we wanted to above 7 GPa, where this kink was really seen in the impedance measurements. Also, the data were not really quite of sufficient quality for quantitative analysis, and that would allow Eric to do the exact same analysis as he had done with the temperature data. So we are continuing to work on this to increase sample sizes and to give even longer exposure times to really allow for full quantitative analysis of these quasi-elastic scattering data. Nonetheless, this is still very promising because we do seem to have a setup where we can achieve pressures to 7 GPa and hopefully soon 10 GPa for QENS. And so with this, I would like to move on to my third topic for today. So now I'm moving a little bit away from hydrides, and I want to talk about the high pressure behavior of germanium. So since I'm changing gear a little bit, let me first introduce the co-workers on this team. We did use a number of instruments. We did some synthesis at SNAP, which I showed you earlier. We also did some in situ diffraction on 1-square, which is a diffractometer at Haifa. So the 1-square team was, of course, heavily involved there. We did the inelastic neutron scattering at ARCS, which was impossible, would have been impossible without Garrett being involved and driving a lot of the ideas and analysis. And of course, then Mary Ellen this has really been her project in a lot of ways to bring the PE cell to 1 square. So she's been involved with all this. And of course, as always, Jamie Mollis and Mark and Matt were, without them, none of these things would happen. But to talk a little bit about why I'm interested in silicon and germanium, let me just give a really brief background on some of the functionality of metastable silicon and germanium that has been predicted in the literature for quite some time, and a lot of studies have been done. So as you may know, silicon and germanium don't just exist in the normal lowest energy diamond cubic structure, but there's a number of other metastable structures that can be recovered to ambient conditions through after high pressure application. So one of those of interest is a rhombohedral structure, the so-called R8 silicon, which has been predicted to have better optical absorption of the solar spectrum than normal silicon. So this here is R8 or silicon 12 compared to the other silicon structures. Furthermore, other studies have suggested that if these metastable structures like the rhombohedral phase, but also a body-centered phase, could be made in as a small hydrogenated nanoparticle, they could enable multiple exciton generation. So all these things could be potentially really revolutionary for solar power conversion, because you end up with structures that are still non-toxic, very abundant silicon or also germanium, but with a better band gap or an altered band gap compared to the standard diamond cubic structures. So this has also been shown that for hexagonal diamond, for example, it may be sufficient to just strain it a little bit to achieve a direct band gap, which again would be advantageous. So the structure I want to talk about today is the so-called ST12 phase of germanium. It's a simple tetragonal structure. There has been a theory that calculated a direct band gap of 0.56 eV, although the fundamental gap appears indirect. This trend has been supported by optical measurements done by Tim Strobel. So the structure has been studied to some extent, but what really has been lacking is inelastic neutron scattering. Inelastic neutron scattering could allow us to directly measure the phonon density of state, and so directly correlate the phonon density of state. We calculate in DFT with a measurement, and this will then really give us confidence that our calculation is 100% correct, that it correlates to the structures we make. And then we could start predicting things. For example, we could start applying shear to see if we can change the ST12 phase or any other structure really just a little bit to have even more desirable properties. And so this is why we set out to measure ST12 germanium with inelastic neutron scattering. So we made a lot of this ST12 germanium phase on SNAP. Incidentally, the PE cell really lends itself to synthesis of the structure because it requires very slow decompression and prefers to be synthesized in the absence of a pressure medium, so in a high shear environment, which really makes for experimentally for a very simple synthesis setup. So with 4 synthesis runs, we made about 500 milligrams of ST12 germanium. Now, this time we had to use the largest VX3 PE cell, which can only be moved around with a crane. It really is a very large, heavy press. It's a 200-ton press. And instead of the single toroidal anvils I've mentioned before, we use double toroidal anvils. So here you see the sample in the middle, and then you see these grooves or toroids, which are used to further support the gasket and prevent blowouts. Now, this synthesis on SNAP was done ex situ. So I really wanted to confirm that we fully metallized our germanium, because these metastable phases I mentioned before are made on decompression. So the way they originate is you start with diamond cubic germanium, so the standard germanium you can get in a wafer. You have to pressurize it to above 12 GPa, where it metallizes into the so-called beta tin structure. So this is the same structure as tin has at ambient conditions. And then this transition is so large that on decompression you do not regain the diamond cubic structure, but instead you make the these interesting structures like the ST12 phase. So to confirm that we made this metallic beta tin, we used 1 square at Haifa for the simple reason that this actually gave us a very good excuse to test how well the PE cell would perform on a diffractometer at Haifa at the high flux isotope reactor. And so here you see the setup. 1 square is 1 square in its scattering aperture is very well suited to the PE cell, which also has a very limited scattering aperture of ±7 degrees. Of course, it was critical to limit the beam size. So here you see the incoming beam was reduced by cadmium slits. And to really minimize or ensure we only see the sample and none of the additional scatter from the anvils and so on. So this experiment was quite successful. Here you see the resulting germanium data at pressures above 10 GPa in the PE cell on 1 square. These doublets here, these characteristic doublets correspond to the beta tin phase. We do have a little bit of diamond from the diamond anvils in there, so we do not have a fully clean diffraction pattern, so we are still working on that. Nonetheless, Mary Ellen was able to refine these data, and based on equations of state, we estimate the pressure was about 15 to 60 GPa on this metallic structure of germanium. But the key was that there was no diamond cubic germanium left. So this really was the key thing we wanted to confirm. This showed us that the synthesis we were doing completely converted all the diamond cubic germanium to the new metastable structure we were interested in. So with this, we then moved on to ARCS, which is a high flux spectrometer with a large solid angle at the SNS, where we measured the synthesized sample. So first, we still wanted to verify the phase composition of the recovered phase. And this here is a diffraction pattern from ARCS. So ARCS is not necessarily set up for diffraction. So we are still working on extracting the data in a way that we can do a full read-write refinement on them. But quite clearly, we indexed the peaks here. And so these black lines correspond to the ST12 structure. And so quite clearly, we see nice ST12 germanium. We also see aluminum, which is because the sample was measured in an aluminum can. So this is a contamination we have to remove with background subtraction. And additionally, it may be that there is a little bit of hexagonal diamond germanium in there, but this is still pending, of course, read-write refinement to really verify. Nonetheless, we went ahead and measured the phonon density of states on this recovered sample. So on ARCS, we chose 3 different incident energies, which can then be refined together, all 3 of them in a multi-phonon software that was developed by the instrument team to one sort of optimized phonon density of state. And this is the result here from our phonon density of state measurement on ARCS. Just for comparison, here is the phonon dispersion on the phonon density of states calculated by Brad Malone and Marvin Cohen. And here is our measurement, which really looks remarkably similar. Please note, we still have not perfected the aluminum background. And as I will tell you later, background subtraction for inelastic scattering really is a key problem we are often still struggling with. But quite clearly, what we see here experimentally matches very well what was calculated. So you may have to turn your head as I keep on doing. Here, this peak here corresponds well to this feature, and this feature here seems to correspond to this one here. So we are very confident that our measurement and the calculation agree so well that we can now attempt further steps to sort of start tweaking the ST12 structure computationally to see what things could be done to give us even better band gap characteristics, for example. Furthermore, it was actually very surprising how fast we were able to obtain some of these data taken on arcs, which encouraged us to also try in situ pressure measurements on arcs in the PE cell. Incidentally, the setup on arcs is very similar to the one on bases. So we were able to use the exact same flange, the same setup, just instead of the medium-sized PE cell, we put on the very large one that we needed to achieve pressures above 10 GPa. Now, this experiment just occurred, so we've only done on-the-fly analysis, but so far this seems very promising. So this here is the raw data from arcs at increasing pressure. And this feature here corresponds to the some of the characteristic phonons in the diamond cubic structure, so in the lowest energy structure at ambient conditions. As we increase pressure then to 1200 or 1400 bar, which corresponds to about 13 GPa, these phonons disappear, and instead we start to see new features, which may be indicative of the beta-tin structure or the metallic phase. I did search through the literature and did not readily find a good DFT calculation of beta-tin germanium. So this is still work in progress. And of course, these are just the raw data. This still needs background subtraction. This still needs conversion to density of state. We also measured multiple incident energies. So this really is very much still in progress. But it was already very promising that we were able to see some evidence of the germanium within the PE cell at pressures above 10 GPa on arcs. So we are most certainly continuing along these lines. And now with this, I would like to talk about final example about neutron spectroscopy on hydrogen that we've really been developing for the last 5 years. So this is work that is being done on the Vision vibrational neutron spectrometer. Vision is optimized for a large range in energy. So it really is the instrument to look at molecular vibrations and, for example, hydrogen under pressure. So this work is done in collaboration with the Vision team, Timmy, especially Luke and YQ. Rainy has designed the cells, and he is pushing that we actually achieve these pressures, or that we achieve the sample volumes, I should say, that we need to do interesting science. And this work is very much still in progress. So initially, or the first step was the development of diamond anvil cells that are optimized for vision, which has a very large, or which requires a very large opening aperture of 120 degrees. So here you see 2 iterations of these diamond cells as they are used on vision. The beam comes here through the gasket, and then you have scatter, forward scatter and backward scatter at these very large angles. These cells are small and portable, so the pressure is applied offline in a press, and then it's clamped in via a simple spring mechanism to ensure that cooling down to 5 Kelvin does not change the pressure. The sample volumes can be up to 2 cubic millimeters, up to 5 GPa, but up to 10 GPa, you're really limited to the 1 cubic millimeter I mentioned earlier as the sort of smallest sample that a lot of neutron instruments can see. So here's an example from the early tests we did on vision, where we studied hexamethylbenzene for the main reason that it's a hydrogenated solid sample. So it was a very good sort of proof of principle sample. And quite clearly, here you see a reference spectrum of hexamethylbenzene, which where a larger volume was measured, compared to the sample measured inside the diamond cell. So this is the green one here, which really replicates very well the same vibrations, even though the sample volume is so much smaller. But then once we increased pressure, things started to look more, I guess the word to use is messy. So here this red signal is at 4 GPa, and here we have higher pressure data. And really, as we learned over time, the problem was not so much that we could not see the sample any longer, but that we struggled with a good enough background subtraction. Now, for those of you who are not familiar with neutron scattering, the typical alignment procedure on vision, and actually a lot of neutron instruments, is a tape measure. So you have your cell here. This is, I think, me, I'm not sure, holding the diamond cell, and we are using this tape measure to estimate whether the sample is at the correct height for the neutron beam. The whole assembly is dangling off this long stick, which you then place into the instrument. So quite clearly, this is not the best alignment procedure for cutting edge, high pressure neutron scattering, where you try to minimize the sample as much as possible so you can achieve high pressures. So we spent, I think, a couple of years really on optimizing that. And our current setup now consists of this large pipe, which is not as bendy as the normal sticks that go into the vision spectrometer or that go into the majority of neutron spectrometers and also diffractometers, actually. We cover the cell in cadmium to really make sure background is reduced as much as we can. We've also learned that it was a key to attach the cell on 2 points here. Typically in neutron instrumentation, you only attach with one center screw, which means you don't have very good control if you're always in the exact same orientation. But with this, we've really gotten a handle now on the placement of the neutron diamond cell in vision. As a next step, we then investigated whether the background changes with pressure. And so here you see a spectrum that was taken with a NIST silicon powder at 0 GPa and 7 GPa. So silicon in such a small sample, is essentially invisible on vision. So all we see here is background due to the diamonds and due to the cell. And quite clearly, there does not seem to be much of a change with increase in pressure. So with all this, we were finally in a position to do a measurement on hydrogen in a diamond cell on vision, as we had been planning for quite a few years. And this here is the result of that measurement of hydrogen measured at 1.25 GPa. So the black spectrum here is a reference solid hydrogen measured at 0 GPa pressure and 5 Kelvin. And the red line here is the hydrogen measured at elevated pressure at the same temperature. There seem to be a lot of interesting things going on in here, which we still try to understand. What is really clear and critical is that we need further pressure points to observe trends and to make sure that features move with pressure, that things are not just due to changes in background, but there really may be interesting insights into hydrogen that may not have been considered in theory quite that much. And I hope to report soon on some more detailed findings, because we do have beam time to continue this and to push the pressure to maybe closer to 10 GPa in November, so just in about a month. Well, and with this, I really want to just give some really simple conclusions, given these projects were quite diverse and tackle different science problems. So I hope I was able to show you that high pressure neutron scattering can be really powerful to study materials behaviors. It's of course particularly useful for hydrides, but also for many other materials in quantum condensed matter or, sorry, or also in geosciences. And as you see, we continue to develop and adapt techniques for high pressure neutron scattering. Sorry, with that, I thank you.
Thank you very much, Bianca. Great talk. It's particularly nice to see all these new technical developments. Thanks for reviewing that. I think many of us aren't familiar with some of the latest. So with that, we have time for questions, and we already have a few in the chat. So let's start with Urshan.
Yeah, I think my question partly is answered by Brent, but I will ask my question anyway to see what
discussion.
Bianca has to say exactly. Thank you for this beautiful talk. It's really illuminating for us who cannot be at Oak Ridge at this time. So thank you. My question was related to the density of states obtained from your measurements, how the elastic peak and how the multi-phonon contributions are eliminated to get into the single phonon density of states.
So to be honest, I think Brent is a lot more qualified to answer that question than myself. So for me, it's working with Garrett, and he uses the get-DOS package, which essentially for me is a black box. So he does the magic to obtain the data. So if you really wanted more details on this, I would recommend looking up that paper I cited, or I could of course also put you in touch with.
No, that's fine. I think
the experts.
Brent led me into the right direction, so I will look into it. Thank you.
Thanks. More questions? The neutron spectroscopy of hydrogen, of course, is something we've been interested in exploring for years, back when SNAP was first proposed. Inelastic work was done under pressure in the Kurchatov Institute way back in the late 1980s. Absolutely stunning work. And I'm wondering if what you're doing now compares with that work that was done so many years ago.
So, as far as I know, I don't know if much work has been done in the past on samples that require gas loading, like hydrogen, and where you need to achieve pressures that are higher than what you can do in a gas pressure cell. So of course, there's been a lot of work done up to sort of 5 or maybe even 10 kilobar. So the data I showed did not exceed that pressure that has previously been studied much, but the cell itself and the setup should be capable of 10 GPa. We just ran out of time on this particular experiment. So really what we are trying to push is sort of new pressure regimes on samples that require gas handling or that need to be loaded with a gas loader like hydrogen. There has, of course, also at ILL, I mean, especially Stefan Klotz has done a lot of inelastic scattering on samples like germanium up to 10 GPa. So that's why we are trying now to basically leverage that we have, that our facility is running at 1.4 megawatts. And so we can try making the samples a little bit smaller and using the double toroids to get above 10 GPa. So we are not reinventing the wheel there, we are just leveraging that we have more neutrons.
The old work from the Soviet Union was on perohydrogen, and I think they went as high as 20 kilobars. And so looking at orthopera separation and those effects going to low temperature will be very important ultimately for that pressure range anyway.
Yes.
More questions?
Could ask one. I think you're right, Bianca, that the whole game here is the background and how to control that. I think the question I have, though, is about collimation. I'm particularly worried about multiple scattering, where you're scattering from the sample into the pressure cell and off into the detectors. You can't just measure the empty pressure cell because you need the sample to scatter it into the pressure cell. You could suppress some of this by collimation, but could you say a little bit more on the ARCS configuration? Did you have any collimators other than the radial collimators on ARCS, or the masking that you put in?
So, no. So this was the first attempt at the PE, using the PE cell on ARCS. So we only used their standard oscillating radial collimator, which removed the pot, the shielding. Sorry, but we are actually developing techniques for 3D printing of radial collimators, especially collimators that are optimized in McVine to really remove, to really be optimized for a given instrument and a given sample environment. This is actually, this collimator project is how I started working with Garrett. So now that we see that these PE cell experiments are possible on ARCS, this is most certainly something that we will adapt to further improve the sample signal. I haven't thought about the multiple scattering that we could use this to remove some of these issues. I'll follow up on that.
10 gigapascals is quite impressive, actually.
Yeah, we were very excited when we realized that we can actually see some of the germanium. Of course, germanium is a very good scattering sample. I think this would be a lot harder with other things, but still, it was exciting.
Great. Dan Shim has a question.
Hello.
Go ahead.
Hello.
Yep.
Yes. Oh, it was a great talk. Thank you so much. I learned a lot. I have a very simple question. Earlier in the talk, you mentioned about effort to form the SiH4 by putting silicon and hydrogen together as a precursor, and you said it wasn't really reacting well enough. Did you actually heat the temperature above room temperature, or if so, how high temperature did you heat?
No, so we didn't. Yeah. So we did not heat for the reason that I was hoping the reaction would happen with the amorphous silicon being a metastable state, plus the amorphous silicon we used is actually nanoporous. So the hydrogen would have sort of penetrated this silicon. There has been actually that work I showed or mentioned by from France, from Michael Hanfland. They showed that even crystalline silicon does react with hydrogen if it's sitting long enough. I think they did have it sitting in a cell for half a year. But really, the key reason why we did not try any heating is that when you move to a neutron diamond cell, your culet, of course, becomes a lot larger, which also gives you a lot more points where you could have potential defects that result in hydrogen fracture. So we found that even room temperature compression with hydrogen is difficult if you scale up to a Neutron DAC. So this is definitely something we are tackling. So this is part of Reiny's project, figuring out how to make our neutron anvils more hydrogen friendly and prevent such hydrogen cracks, even with these very large areas that give rise to so many defects.
Yeah, that's pretty fascinating challenge that I never thought about before, but that's really interesting. Thank you.
Thank you. Well, a lot of these challenges we're only finding as we are trying things. So we are learning as we do these experiments.
You are really at the front line.
Oh, thank you.
That's right. Thanks, Dan. More questions? Okay.
Yeah, this was a lot of sort of diverse work to digest. So if anyone wants to follow up later on, please feel free to send me an email or contact me in some other form.
Do you want to spend maybe 30 seconds describing the new initiative and what's on the horizon for the second target station?
Okay, sure, great, thank you. So for those of you who are not that much involved with neutron scattering, there is current there's plans, or there will be a second target station at the SNS campus. So the current instrumentation will be complemented with the second entire target building, which will give space to another suite of instruments that complements the existing first target station and also HIFA. And currently they are collecting preliminary proposals. The deadline is next week for the first suite of instruments that will go into this entirely new target building. And one of the instruments we are working on, or that we are proposing, is, the working title is Titan. It's an instrument that is specifically dedicated for extreme environments. So it will be a platform where we can leverage combinations of high magnetic field and high pressure. We hope to really push high pressure spectroscopy by having a spectrometer that allows us more easy access for alignment, and so that some of these background problems go away. So if you are interested in some of the science, please contact me if you have some ideas of things you would like to try with neutron scattering that are not possible in current instrumentations. Yeah, also please talk to me. We are, this whole concept for an extreme environments instrument really came only about a month ago. So we are still very much defining what, how far we want to go, and we really want to push the envelope on all forms of extreme environments really with this instrument.
No, that's great. Well, thank you.
Hey.
Wonderful talk. Thank you all for joining us, and we'll see you next week.
Yeah, thank you everyone for listening in. And thanks again, Russ, for inviting me.
Sure.